All right, but as always in trigonometry, there's another way to do it. So here's another approach to this same problem. Tangent of theta is -1/2. We know that's the ratio of y to x for coordinates x and y on a circle of radius r. So what I can do is I can take the y to be -1 and the x to be 2. And so I have a terminal side, or excuse me, a point on the terminal side of theta is the point 2 comma -1. So there's the initial side of theta, and there's the terminal side of theta, containing the point 2, -1. Now I can go back to the definitions of sine and cosine on the circle of radius r. And I know that the cosine of theta is x divided by the square root of x squared plus y squared. So in this case, the x is 2 over the square root of 2 squared plus -1 squared. This gives me the cosine of theta is 2 over the square root of 5, which once again you can rationalize to 2 square root 5 over 5. Once I get the cosine of theta, I can get the secant of theta, which is 1 over the cosine of theta. And if I'm going to flip this over, I might as well just flip that over to get the radical 5 where it needs to be radical 5 over 2. The sine of theta is y over the square root of x squared plus y squared. So the sine of theta is going to be -1 over this square root, which we've just found to be radical 5. And so this gives us, when we rationalize the denominator, negative square root 5 over 5, which means that the cosecant, which is 1 over the sine, we take the reciprocal of this, that's going to give us negative radical 5. And last but not least, the cotangent of theta is x over y, which in this case is 2 over -1, which is -2. So whether you go the identity route or this route or some route of your own, it doesn't matter as long as what you're doing is mathematically correct. And that'll do it for number 2, part A. Okay, in part B, we're asked to find the sine of theta plus pi. Okay, now how are we going to do that? Well, we'll go back to some of the geometry here. Now, how do we figure this out? Well, remember when we think of adding angles, we think of going the first angle, and then the initial side of the second angle is the terminal side of the first angle. In other words, if I want to graph theta plus pi in standard position, I graph theta, which is what I did, and then from the terminal side of theta, I rotate counterclockwise pi radians. So there's pi radians. So this is the terminal side of theta plus pi. Now, the reference angle for theta, by definition, is this angle here, which I'm just going to temporarily call alpha. And because we have a vertex angle, the angle here is the same as the angle here. So what's that mean? That means that the sine of theta plus pi is going to be the same as the sine of the reference angle alpha, because it's a quadrant 2 angle, which is the exact opposite of the sine down here. All right. In other words, using just reflections, the point on the unit circle on the terminal side of this guy is the reflection through the origin of the point of the unit circle on the terminal side here. So that means that the sine of this guy is the exact opposite of the sine of theta. We work the sine of theta out to be negative square root 5 over 5. And so we get the sine of theta plus pi is positive square root 5 over 5. All right? So without even knowing theta, I know what the sine of theta plus pi is just using geometry. That'll do it for part B. All right, number 3, we're asked to solve the secant of theta is negative radical 2. All right, now when we're given an equation involving a secant, we usually convert it to cosine. That means the cosine of theta, which is 1 over the secant of theta, is 1 over negative square root 2, which is negative square root 2 over 2. Where's this going to happen? Well, the cosine is negative in quadrants 2 and quadrant 3. Since the cosine is negative square root 2 over 2, I know that means the reference angle here is pi over 4, as is the reference angle here. So 1 quadrant 2 angle with the reference angle of pi over 4 would be 3 pi over 4. I can think of 3 pi over 4 as going halfway around, which would be 4 pi over 4, and then backing up a pi over 4. Quadrant 3 angle with the reference angle of pi over 4 is 5 pi over 4. Because going halfway around is 4 pi over 4, and then I'm adding another pi over 4. So my solution then, theta is one of two things. It could be 3 pi over 4 plus any angle coterminal with him, or theta could be 5 pi over 4 plus any angle coterminal to him. And once again, these are good for all integers k, and so on. All right, so that does it for number 3. And number 4, we're asked to solve for t. Cotangent t is radical 3. Normally when we use the variable t, we're talking about real numbers here, but once again, real numbers correspond to angles measured in radians. So where is the cotangent of t positive? Well, cotangent is positive in quadrant 1, as well as quadrant 3. Since the cotangent is square root 3, I think back to my known values for cotangent. This tells me that the reference angle is pi over 3. Excuse me, pi over 6. All right, so one angle one quadrant 1 angle with the reference angle of pi over 6 is just pi over 6 itself. The angle in one angle in quadrant 3 with the reference angle of pi over 6 would be pi plus pi over 6, so that would be 7 pi over 6. Now, as we've mentioned before in class, with tangent and cotangent, the two answers we get are always pi units apart. Geometrically, if I look at the terminal side of these guys, they're exactly pi units apart. All right, that means I can generate all the solutions to this by starting with pi over 6 and then adding multiples of pi. Adding pi gets me to 5 pi over 6. Then adding pi again gets me back to 13 pi over 6, and subtracting would take me backwards this way. So with tangent and cotangent, these values are always pi units apart, and that lets us simplify the solution. T equals pi over 6 plus pi times k, for k is 0, plus or minus 1, plus or minus 2, and so on. So that'll do it for number 4.